Check. Alright, this is a demo where I will be teaching a class on momentum. This is going to be my first attempt at teaching. So we're gonna learn about momentum by understanding the law of conservation of momentum. Now we all know momentum, which is normally symbolized by the letter P, is equal to mv, which is mass into velocity of any body, of any particle. So when we are trying to understand law of conservation of momentum, the thing we need to remember is that the initial momentum of a body or a system is always equal to the final momentum. That is, m1 v1 is equal to m2 v2, which is always in terms of net, which is the entire system. It is not just considering one particle but the entire system. So now let's use this example in understanding recoil. We know what recoil is. When you fire a bullet from a gun, let's assume, I'm bad at drawing, but let's assume this is a gun and that's the trigger and there is the bullet inside. So now initially the system is at rest. So this is your initial and the system is at rest. So the velocities are equal to 0. So we have momentum P net initial is equal to 0, and then now we have fired the bullet. So what happens inside the gun is that there is a collision between the part of a gun and the bullet, which causes the bullet to move forward with a great velocity because we make the mass of the bullet small. So what happens is now we have a gun, the same gun, and the bullet's been fired. So the bullet is somewhere here and the bullet is moving with a great velocity ahead. So let's assume that is VB, but the gun VG has to recoil because we know that when we fire a bullet the gun moves back a bit. Now when guns were originally created, it goes back in the 15th century. When the first guns were created, the technology was not very efficient to have the bullets moving fast. So what they did was they tried to make the gun very heavy, and when the gun was heavy they minimized recoil. So let us mathematically understand how that works, that heavy guns try to minimize recoil. So now we know that the P momentum net of the first initial system was 0, and the momentum of this system, which is this part where the cursor is pointing, that P net final, because this is the final system and this is the initial. So the P net final will be equal to m of the bullet multiplied by the velocity of the bullet, which is in the forward direction, subtracted by m of the gun multiplied by the velocity of the gun. The reason it is being subtracted is because the gun is moving in the opposite direction. So because of the 180-degree difference between velocity of bullet and velocity of gun, mathematically it becomes negative by vector notation. Remember, momentum is a vector where velocity is a vector. So it is always, the P momentum is always in the direction of the velocity. So if two momentums are in the opposite direction, they need to be subtracted, and if they're in the same directions, they're added. So coming to my first point, LOC of momentum, the initial momentum and the final momentum have to be equated. So let's take initial momentum and the final momentum and let's equate them. So 0 is equal to mb vb minus mg vg. So when we bring this mg vg, which is the momentum of the gun, to the other side, we get mb vb is equal to mg vg. Forgive my handwriting, I'm still new with this software, but it will get better soon. So this implies, this symbol means implies. So my equation mb vb is equal to mg vg implies I can divide both sides by mg and divide both sides by vg. So, and when I bring it to the other side, this is what I get. And this is the equation I'm going to be considering to explain to you. Since I've derived this equation, I will use this to explain to you why the gun's mass has to be very large to minimize recoil. Now we know the mass of the bullet is very small compared to mass of the gun. So mb by mg, let me write it up here. Okay, I'm writing it here after. Now we know that mb by mg, because mass of bullet is much smaller than the mass of gun, is going to be less than 1. So similarly, Vg by Vb will be less than 1. So this goes without saying that the velocity of gun has to be less than the velocity of the bullet. But to minimize recoil, we want the velocity of the gun to be very small. So let's say nearly equal to 0. So if it is very small, the velocity of the gun, that is how we're going to minimize recoil. But that is the condition to minimize recoil. So if we can put Vg almost equal to 0, which is that the velocity is very small, which then tells us that the mass of the bullet has to be much smaller than the mass of the gun, because these two equations are equal. These two parts of the equations are equal. So this shows us why guns have to be quite heavy in order to minimize recoil, and which is a lower velocity of the gun moving backwards. So this was used in the olden days when the guns were so heavy that they had stands, and they had to be carried around with their stands because it was impossible for a person to lift these guns. But nowadays we have better technology. We use springs and which minimize shock absorption, and so our guns have become lighter with better technology. But using the simple principle of conservation of momentum, we can prove why guns have to be heavy from the before equation. This can also be applied in the case of an exploding bomb. Now in an exploding bomb there are parts. Let's say this is a bomb and it is set on fire, and until it comes here it's going to explode. So now what the bomb does, it explodes in parts. So now let's say there are 3 parts to this one, and this is the initial state, and this is when its net momentum P net, which is initial, is 0, because there is no velocity to any of these 3 particles. Let's name it 1, 2 and 3. But after some time, what happens to this bomb, which is soon going to burst, these 3 parts roughly move in all different directions. I'm trying to draw the paths roughly, and each of these paths then holds devastating value because it has so much velocity, and they all move in different directions. So what one has to do is to resolve all these vectors, and effectively they have to come to 0. So this is V1 for the first part, V2 for the second part, V3 for the third part, and let's say the first masses are like that. So it's P net, which is final, will be equal to m1 v1 vector, that is the most important, plus m2 v2 vector plus m3 v3 vector. Now when we are equating all of these, they have to be equal to 0 because of law of conservation of momentum. So m1 v1 plus m2 v2 vector plus m3 v3 vector is equal to 0. This is your final equation. But we know that based on vector algebra, this can only be equal to 0 when these vectors they have a large angle between them such that the cosine of at least one or two of them become negative, so that the net resultant is 0. Which is why an exploding bomb is always split into parts that move in different directions. Its parts can never move in the same direction, otherwise, or directions whose angle is very small, because here the three vectors that we see have large angles. Let me just draw the three vectors having a common point. That's your V2 and that's your V3. So as you can see, the angle between these two is quite large. Now V2 could have gone this side, it could have gone like this. Let's just say these are all hypothetical examples of V2. So even here the angles are quite big if you see the thetas. This shows that only when cosine will become negative will this equation ever be true, and therefore it is impossible for parts of an exploding bomb to move in angles that are close to each other or to move in one direction. They will always move in different directions. This is how we apply the law of conservation of momentum in examples of recoil, because this too is an example of recoil. This is the first part of law of conservation of momentum. After this we have elastic collisions and we have inelastic collisions, which we will be discussing in the next part. Thank you.